Hello everyone, I welcome you all to this online classes. Today we are going to discuss about inductance and types of inductance and their expressions we are going to see. So in the last classes we discussed about Faraday's law and Dunn's law, so which says that the EMF, induced EMF in a coil is equal to time rate of change of magnetic flux. So once again we will see Faraday's experiment 2. What is Faraday's experiment 2? So suppose if you have a coil C1 which is connected to a galvanometer, and close to this coil C1 there is one more coil C2 and which is connected to battery. So now, because if it is connected to a battery, the current flows in the coil, and now the coil behaves like a magnet. So it's a solenoid. Solenoid is nothing but simply like a magnet producing a magnetic field. Now by moving the coil, keeping the coil C1 constant, moving the coil C2, the magnetic flux lines passing through C1 is changing with the time. So if there is a change in flux with the time, there is an EMF developed in the coil C1 given by E1 is equals to time rate of change of magnetic flux is nothing but EMF. So this EMF is produced because of the flux change due to coil C2. So this EMF is due to the flux change produced by other coil. So this phenomena we call it as mutual inductance. The induced EMF and the induced current in coil 1, the induced current developed in coil 1 now is due to the flux change produced by the coil C2. So this phenomena we call it as mutual inductance. Mutual inductance, which is represented with the symbol capital M. Capital M. So the induced current in C1 is due to flux change produced by other coil C2. So this phenomena we call it as mutual inductance. Now let us consider only an isolated coil C2. Right. So we have a coil C2 having n number of turns. Now this coil C2 is connected to an alternating voltage source. What is meant by alternating voltage source? Where the voltage and current changes sinusoidally with the time. So if you consider the current in the source, if you consider this is providing a current which is varying with the time. Whereas in case of a battery, the current is always constant. So if you consider C2 coil connected to an alternating voltage source, it means the current is varying with the time. If current is varying with the time, the magnetic field produced in C2 having n number of turns. The magnetic field of a solenoid is given by mu naught n into I. If I is constant, B is constant. But here it's I is varying with the time, so B is also varying with the time. So, and flux is nothing but B into A. So B, the area of the solenoid loop is same, but what is changing with the time? B is changing. So there is a change in flux. There is a change in flux in coil C2. Why we have change in flux? Due to the alternating or varying current flowing in the same coil. The current is also flowing in the same coil, and the alternating current produces changing variable magnetic field, and because of the variable magnetic field, so B is variable. So if B is variable, magnetic flux is also changing. This magnetic flux is also a function of time. So in the same coil, as it is connected to alternating source, B is changing, flux is changing. So if there is a change in flux, according to the Lenz's law, there is an EMF developed in the same coil itself. So in the same coil E2 itself, there is an induced EMF and there is a induced current, which is because of the variable current flowing in the same coil. Here the current in the coil C1 due to the C2 coil, whereas here the induced current in C2 is because of the current flowing in the same coil. It is called self-inductance. It is called self-inductance. So now, by considering all these things, so we are going to derive, we are going to understand what is mutual inductance, self-inductance, and we are going to derive different formulas for mutual inductance and self-inductance. Right. So first of all, we'll see the basic thing that we know from the Biot-Savart's law. What is Biot-Savart's law? The magnetic field, if a current is flowing in a conductor, the magnetic field at a point P is given by B is equals to mu naught by 4 pi into IdL by R square. So the magnetic field is directly proportional to current, or directly proportional to the line segment, inversely proportional to square of the distance. So from this we can write that the magnetic field is directly proportional to current. Let us say this, we'll write current as capital I. So B is directly proportional to the current flowing in the conductor. Right. If B is directly proportional, then what about the magnetic flux? Magnetic flux is nothing but B into A. So magnetic flux is also directly proportional to current I. Right. So suppose if you have a coil, whose geometry, whose area is not changing with the time. So in this case, and current is changing with the time. So we know that phi B is nothing but B into A. If keep the geometry of the coil constant, that is, if geometry of the coil is not changing with the time, that is, A remains constant. So here, as B is a function of current, as current changes, B changes. As B changes, the magnetic flux also changes. It means as I changes with the time, the flux also changes with time. That is, by considering the differentiation of this equation with respect to time, so d phi B by dt is also proportional to di by dt. What it means? So phi B I consider B into A. So differentiation, if I consider, if A is constant, dB by dt, what is B? B is directly proportional to I, so di by dt. So the rate of change of flux is directly proportional to the rate of change of current. Right. So this is one of the equation which we are going to see. Right. So from the Biot-Savart's law, B is directly proportional to I. So as B directly proportional to I, the magnetic flux is also directly proportional to I. Now consider the time variation, differentiation of this equation, keeping area of the loop constant. So differentiating this magnetic flux with the time also means dB by dt. So d phi B by dt is nothing but di by dt. Right. Now in place of a single turn, let us consider a coil in which we have a closely wound n number of turns. In that case, so if you have a coil with n number of turns, so the magnetic flux linked with each turn, if it is phi B, the magnetic flux is changing with each turn. For one turn, it is phi B. if I have a coil having n number of turns, so the total magnetic flux linked with this coil is given by flux linkage. When we use this term, if the coil having n number of turns, each turn will have a flux change of phi b, produces a EMF E. If I have n number of turns, there will be n phi b flux, there will be an induced EMF. So the flux linkage, if we have n number of turns, n phi b, if phi b is directly proportional to current, the flux linkage is also directly proportional to current. More is the current flowing, so more will be the magnetic field generated, more will be the magnetic flux linked with the coil. As the current through the coil increases, this is the applied current. What we are applying, giving through battery. This is the voltage which we are giving through battery. Right. So as the current increases, the magnetic field increases, B increases. As B increases, the magnetic flux, nothing but B into A, so magnetic flux linkage also increases. So N phi B is directly proportional to I. Now, by removing this proportionality and introducing a constant, proportionality constant, which is nothing but L into I, where this proportionality constant L is called inductance. It is called inductance. And this L is depends on the geometry of the coil. That means it depends on the number of turns and the area of cross section, length of the coil. On all these factors, this inductance, capital L, depends on the geometry of the coil, and it also depends on the intrinsic material properties. Suppose here this coil is in air, but to increase the magnetic field, we can introduce an iron rod in the solenoid so that the magnetic properties enhances. So L also not only depends on the geometry, it also depends on the intrinsic material properties. So magnetic, if I introduce a soft rod or a ferromagnetic substance, so magnetic flux will be more, so flux will be there and EMF will be there. So in that case, the inductance depends on the external geometry and also depends on the material properties. So this L, which is nothing but the inductance, L we can write it as magnetic flux linkage per unit current. This is the formula for the inductance. So observe this equation. In the capacitance, we have capacitance. In the 5th chapter we discussed electrostatic potentials and the capacitance, where we considered the charge on the capacitor is directly proportional to Q, is directly proportional to the potential difference V, and this proportionality constant is Q equals to CV. So that equation what I have, which is resembles N phi B is equals to L into I. So in the last class we discussed the energy consideration, where we said that there is a relation between the charge and the magnetic flux. What is this? This delta Q is equals to delta phi B by R. So the magnetic the charge and the magnetic flux, and the V is the potential difference, and here it is current. So what is the parameter which is equivalent? L. For the equivalence is capacitance in electrostatics is equivalent to the inductance L. So here we know that the capacitance of a capacitor parallel, suppose if we consider a parallel plate capacitors, each is having an area A and they are separated. Suppose if they are separated by a distance of D, in that case, and if suppose if we introduce a dielectric slab in between the parallel plates, so the capacitance of a parallel plate capacitance is given by K into epsilon naught A by D, where K is the dielectric constant of the medium between the plates, and A is the area of the plates, and D is the distance. So capacitance depends on the geometry and the material medium. In the same way, the inductance also depends on the geometry of the solenoid and also the material medium which is present in the solenoid. There is a similarities between the capacitance. In electrostatics we have capacitance, in magnetostatics we have inductance, right? So now what are the units and dimensions for inductance that we will see. So here L is a scalar quantity, it's a scalar quantity, and the dimensions for the inductance. So what is inductance? Nothing but the magnetic flux per unit current, right? L is equal to magnetic flux means BA by the current, right? And what is the units of B, magnetic field? We can write this as Newton per meter ampere into area of the loop. This is the magnetic field unit, Newton per meter, into current unit is ampere. And here the area, which is meter square, by the unit of current is ampere. So by rearranging, we can write this as Newton meter per ampere square. And now we'll write the dimensions. So we can write this as magnetic flux per unit area, right? This is magnetic flux per unit area. So first we will see the dimension part of it. So Newton is nothing but m power 1, L power 1, T power minus 2 into L power 1, and the current is, unit of current is ampere square, right? So the dimension of inductance is m power 1, L power 2, T power minus 2 and ampere power minus 2. This is the dimensional formula for the inductance. And what is the unit of inductance? So the unit of inductance is given by magnetic flux per unit current. L is nothing but magnetic flux per unit current, right? So the SI unit for this is, it is Henry. So who is this person who discovered electromagnetic induction in USA? Yes, Faraday also invented this in electromagnetic induction, but these two people are at different places. So in the honor of Joseph Henry, the SI unit of inductance is Henry. So what is Henry? Magnetic flux, we said that it is Weber per ampere. So Weber per ampere is, we can also write this as Henry. So this is about inductance.